So let's talk about fixed point. We talked about arithmetic of binary representation where we had signed and unsigned, representations of binary. We said with the unsigned version, when we have n bits, then we can, have a range of 0 to 2 to the power of n minus 1. And then when we are considering the signed version, the range is going to be less, basically, because we are covering, or shifted, because we are covering the negative ones too. And remember that for negative numbers, we are using the 2's complement. That's what we mainly talked about yesterday. Now getting into fixed point, okay? For fixed point representation, we have to declare what is the format, okay? And for that, we use qm.n for fixed point. Because remember that your computer has no idea. It's just like in the registers, in whatever memory locations, all you have is 0 and 1s, right? We'll cover it later. It's your responsibility and the program you are writing to interpret those numbers correctly, okay? So qm.n is a way to show like where do I want the binary point to be? For example, in decimals, when we say 1.43, this is our decimal point, right? And in binary, we call it binary point. So if I have a string of 1101, let's say, I want to say the binary point is here. That means I have only one bit of integer. The rest of it, consider them fractional. Okay? Or I could be saying the same number, but now 2 bits are the integer and 2 bits are the fractional. And these are two completely different numbers. When we translate them, interpret them to decimal, they're completely different, okay? But you have the option of declaring that, saying like, okay, where do I want this binary point to be? So whenever we use q as opposed to uq, it means it's a signed fixed point, okay? So in this course, whenever you see q, assume that you have 1 bit for the sign, and that is the beginning, the MSB bit, okay? So in total, we would have m plus n bits. Now, for qm.n, we have two interpretations, two notations basically. One of them is Texas Instrument, where it says, where it considers whenever they use q, the 1 bit that they use for sign is implied. That's why when you add these numbers, it's going to be basically 15, this is 15, this is 31. But you have to add the 1 bit that is for the sign because that's implied, okay? So you can see here that Q015 means we have 1 bit for the sign, again, because it's implied, then 0 bits for the int, 15 bits for fractions. Next, 7.8, 1 bit for the sign, 7 bits for the integer side, 8 bits for the fraction, and 15.16 the same. So we have in total 16 bits, then 16 bits, and then 32, and those are the scale factors that you would see. So, but ARM, there is another notation that it says no, nothing is implied. In this version, m that I put here, m is always 1, which is for the sign bit, plus the int bits. So if you add m plus n, that's the total of the bits that you get. So that's why m in this notation always has to be, if it is qm, it has to be always equal or more than 1. We can't have 0 in this notation. In this course, we will use ARM notation, but for some of these standard ones, If you see Q7.8 or 15.16 or 0.15, just assume that they're equivalent to their ARM notations of 1.15, 8.8, and 16.16, because these are the standard ones. If you see anything other than these, consider that M has the sign bit and the int bit together. Just because even in the textbooks or even in online resources, you would see these two being used interchangeably. So I wanted you to be familiar with it. Okay. Now, the way we get the equivalent version is that it's super easy, because you say if I have n bits of fraction, okay, then all I'm doing is that I'm multiplying whatever number I had in binary, in integer, by 2 to the power of minus n. Just like we said yesterday, if I wanted to represent 1.43, I could have said, and this is, let's say, this is decimal, right? This is decimal. I could have said this is 143 to the power of 10 to the minus 2, right? I could have said it the same way. So here, whenever we are saying fixed point has n bits of fraction, we are basically saying the integer, there is an integer value that can be multiplied by 2 to the power of minus n. So for example, let's go through this example one more time. So we have 0x. Whenever we show 0x, that's a hex number, okay? That means that everything you see here translates to 4 bits. So if you have 0x4000, that means the binary, I'm not going to read all of these zeros, but that's what the binary looks like. Okay, now let's interpret this. Okay, so we have, I know I have it here, but I want to write it so we know. 1 0 0 0 0 0 0 0 0 0 0 0. Okay, so we said this is, and remember, this is Q1 15. So we have in total 16 bits. We have 1 sign bit, 0 integers, and 15 fractional bits. Perfect. This is my sign bit. And then right away, it starts the fractional bits. Okay. Now, so since this is 0, this must be a positive. Now, in order to get the fractional bits, all you do, consider this an integer. 100, this is basically, you can say 16,384. And then now you multiply this by 2 to the power of minus 15. So you get half. Another way to look at this is, okay, I'm going to write this again. It says the fractional starts right here. That 0, be careful. It doesn't mean our integer is 0, it's our sign, okay? But our integer, our fraction starts right after this one. And then the other way you can do this to say, if I had a first bit here, I would say that's 2 to the power of 0, right? When you want to do this, it's 2 to the power of minus 1, minus 2, minus 3, and you move to 2 to the power of minus 15. So you see, by multiplying this over here, this is basically 1 multiplied by 2 to the power of minus 1, which is 1 over 2 half. So some of these, it's easier to just, do the second way to calculate the fractional one instead of scale it by multiplying the integer number to the 2 to the minus 15. For example, if I had this as 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, how much would this be? In, again, Q115 format. What should I do? Go ahead.
So you would just add 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3.
Exactly. That's 0.5, 0.25, 0.125. And that's going to be 0.0875. Okay? So for some of these, it's easier to just do it this way, especially if, the most significant bits are the ones that are ones, basically. Okay. Again, why we are learning this? Exams. Okay. So, let's, no, then there is a point. I'm kidding. There is a point here, like later you'll see. So now, let's move on to this one. We have 0x f, f, f in 4 f's in Q115, okay? So again, we have 1, 1, 1, 1. Let's look at this together. It's Q115. We have 1 sign bit, 0 integer bits, 15 fractional bits. Okay? So first thing I do is to find that sign bit. So here, 1 is the sign bit. And then the rest of this is the fractional bits. Right? It says sign bit is 1. That means, is it positive or negative? Negative. Perfect. And again, before going to the fractionals or calculation, treat this binary just like an integer binary, okay? Don't think about the fixed point. So if this is a negative number and the rest of these are just integers, for a second, just consider these integers, how would I calculate the value? We have to consider 2's complement, right? For 2's complement, I have to flip them and then add 1, right? So this is a minus number. I'm going to flip them first. So 2's complement. It's going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. How many zeros? Okay, one more. Right? Then I add 1 here, plus 1. So that's going to turn this one to just 1 here. Okay, so our number is actually minus 1. Now the second way we learned that 2 to the power of minus blah, 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 all of that is going to make it very hard. So because we have lots of 1s here, but minus 1, you can multiply it by 2 to the power minus 15, and then say, okay, this number 517, you see the number here, 10 to the power of minus 5. So it's a very, very small number that you're showing with 16 bits. Any questions on this? No? Now let's go do the reverse. How can we do 0.625 in Q150? 1.50. Okay? Since we know we have to have one sign bit and no integer bits, right? Since this is positive, it's going to be 0. It's a positive number. Now I start the fractional. I can easily say that 0.625 is 0.5 plus 0.125. And this is 2 to the power of minus 1 plus 2 to the power of minus 3. So I say this is 1. This is my point, where my point starts. 0, 1, then 0, 0, 0, 0, 0, 0, 0. What did I get? This is my string. I need to convert this to hex. It's going to be 0x. What is this number? 5. 5, 0, 0, 0. Right? Or you can do it another way. Say, I add, this is the first method, which is similar to the second method we used the other time. The second method is, okay, I'll do 625 multiply 2 to the power of 15, because that's how many fractional bits I have. And then this is going to be 20,480, and then I'll just show this as binary. Right? But like sometimes with some of these numbers, like it's easy to decompose it to the power of, 2 minus something. So you don't have to get the calculator and calculate 2 to the power of 15 and stuff like that. Right? Okay. Now, let's talk about, you've seen it here, Q115, for example. We saw a very small number that we showed right here, minus 3 point something, 10 to the power minus 5. Then we can even have large numbers with this representation, right? But what is the range that you're covering? It's very important because based on your application, and based on how much, the range of the sensor readings or the resolutions that you need to know what format you should be using, right? So you can basically, without overflowing, without saturation, you can represent all the readings you have successfully. So we have two things with QM.N format. One of them is resolution, and as you know by now, it's 2 to the power of minus n. Then the other one is the range. And as you can guess, for a fixed amount of bits, number of bits, right? If you increase the fractional bits, n goes higher, resolution goes lower, means resolution goes, how can I say it? Better, because I don't want it to get confusing. Then, but m has to come down because the number of bits you have is constant. And when m comes down, then range comes down. So you're covering a smaller range. So you have this trade-off that you have to consider when you're deciding between resolution and range. Now, let us look at an example. Are we good? Any questions so far? Okay. Let's look at an example. Well, first look at this and then the example. Here, again, I said like this Q7.8, this is basically Q.8.18 in ARM. The same thing for this one. It's exactly Q16 in ARM. Well, this is UQ. Remember this one. And these are correct. So when we have Q7.8, our resolution is going to be 2 to the power of minus 8. And our range is going to be 2 to the power of m minus n, right? 2 to the power of, what was the other one? 2m minus 1 minus 2 to the power of n. Did I get that right? Yes. So this is our general formula for the range. Here we have 7 integers basically. And here we have 7, this is 8. So you can see that. No, something is wrong. There should be a minus here. Oh, there is, okay, yes. So this is a very small number, and then that's going to be reduced from 128, right? Just looking at this, you see the number of bits between Q8.8 and 1.15 are the same. But as you increase n, resolution gets better. You have, finer steps between your readings. But look at the range, how range looked. We went from about 256 to only 2. So your readings got to 2. Are we good? Yeah? Okay, so as we said, when we are interpreting these bit patterns, it's really important to remember the format, because the same bit pattern, right, with a different format can be interpreted as a widely different number. So yes, the hardware keeps that bit format for us in memory locations, but it is going to be it's going to go through an interpretation layer at the software level, so that we know like what this number corresponds to. Does it make sense? So all you have in different memory locations, let's call it this. All you're going to have is these numbers. You don't know what this is. This is signed, unsigned, fixed point, floating point, whatever, you don't know. And it's matter of interpretation and being consistent with the formats that you're reading. For example, we have an unsigned 8-bit integer. Let's say the value is 236. How does that look like? 236. Does anybody remember? No, not remember. Can you say it? If it's 8-bit. I don't know, so you say it. It's 128, right? Plus probably 64. Then what else? 32. It's minus 20. So 20 is 16 plus 4, right? So we can say this is 1 out of 4. Zero. There is no 4 in it. So this is 0, then 1, then 0. Does that look right? Anyone? Okay, anyway. So when we get to the signed one, because we interpret one of them as the sign, right? Then we are left with the first one, this is probably 1, is going to be the sign, and then the rest of it is going to be interpreted as the integer value, right, that we are reading. Do you want to say it? Yes, please.
Yeah, I think it's 110.
Uh-huh.
Sorry, 1110.
1110, okay.
Yeah, and then 1100.
1100, okay. I wasn't even close, was I? No. Okay, so here we get the first one to be the sign, right? Now we have to calculate the 2's complement. So it's going to be 001, 0011, and then add 1 to this, which is going to be 1. Add 1, and this is flip. And then 0, 1, 0. Sorry, 1. No. 0, 1, 0, 0. So this is minus 20. Okay, so this is the number. What if it was Q4.4? Then we say, okay, 1 bit is the sign, 3 bits are the integer. So let's look at this again. What if we had this one? 1, 1, 1, 0, 1, 1, 0, 0. So again, this is our in Q4.4. These are our ints. These are our fractions. And these are and this is our sign. So we can say it's minus 20 multiplied by 2 to the power of minus 4, which is going to be minus 1.25. If it was Q8.0, then that's similar to the signed one. So whenever the fractional part is 0 bits, then that means it's treated as a signed binary. It's very equal to that, right? And then the ASCII version is completely different. So the interpretation is different. So that's the importance of keeping the format, knowing what the format is, and interpreting that correctly. So for example here, when we are doing addition, subtraction, or accumulation, usually what we do in order to remove the risk of overflow is that we have a middle step here. So when you are summing two numbers, right? Two numbers in 16-bit, in order to make sure overflow doesn't happen, right? What you're doing, instead of keeping track of, okay, is this number small enough, or these numbers are small enough to be summed up, and then their summation would fit in like a certain number of bits. What you're doing is that you sum it up, you put it in something bigger, like 32 bits, you add 2 16 bits, put it in 32 bits, and then check that 32-bit content to know if overflow has happened or not. All right? So this is a very good practice to have that middle step. And like sometimes the modern ones, they do that automatically. But if they don't, and you have to check that, you need to do that yourself. Because if overflow happens, that number that you got has nothing to do with the number you wanted or you expected. So, and then for addition, what is important for you to know is that you're multiplying two different formats, or let's say any formats, qm1.n1 multiplied by m2.n2, then your result is going to have the summation of the integer bits as their integer bits, and then the fractional bits add up too. For example, if you multiply Q1.15 by 1.15, the result is going to be 2.30. Okay? And then if you interpret that as 2.30, so you should know that, right? If you interpret that as 2.30, then you would get the right answer. But if you don't know that and say, oh, I have two Q115, 1.15s multiplied by each other, I'm going to interpret this as Q. I know it's going to be 32 bits, but I'm going to interpret this as, 1.31, for example. Then this would be completely wrong result, right? So you have to know what your result, what format of your result should be, and interpret it accordingly. Any questions? No? Okay. Let's solve this one. It says, interpret the 8-bit pattern of this as a signed Q 3.4, okay? And this is, again, like, with these standard bit sizes, treat this as Q 4.4. And express the result as a decimal value. So what should I do? First thing I need to do is to separate signed bits, integer bits, and the fractional bits, right? So let's do that. I have 1, 1, 1, 0, 1, 1, 0, 0. What is the sign? So first, this is our sign, and it is a negative. Then how many integer bits do I have? 3, yes. This is my integer bits, and the rest is our fractional bits, right? So this is a -1. So I need to look at all of this. Let's look at it for a second as all as integer, and then find out what is the equivalent decimal value. Since it's a negative, I have to find the 2's complement, right? So I need to flip all of this, say 1, 0, 0, 1, 0, 0, 1, 1, right? And then add 1, second step, then 0, 1, 0, 1, 0, 1, 0, 0. And that is going to be our infamous minus 20. So this is 20, and then I have a minus here, so it's going to be minus 20. Once I got that, then multiply this to the power of minus 4. So minus 20 over 16, which is going to be our minus 1.25. Okay, so this was simple. Now let's go to the next one. It says multiply 0.625, which is in 1.15 format, by minus 0.75, which is again in 1.15. Show the raw 32-bit product, apply rounding to return to 1.15, and give the final the result in hexadecimal or decimal. Okay? So what should I do? Are you still with me? I'm tired of 0 and 1s? So by now we should know 1.625 in 1.15 how it looks like. Do you remember?
1, 0, 1.
So it's 0, 1, 0, 1, 0, 0, 0. This is our 0.625. Now, minus 75. That's the pretty one, I guess. So for minus 75, let's do this. First, let's find 0.75, okay? Then we calculate the 2's complement, right? Okay. So for minus 0.75, Okay, so for this one, what we have is, we can say 0.75 multiplied by 2 to the power of 15. We bring it to integer, that's going to be 24,576. And then we make this to minus 24,576 by calculating the 2's complement of the positive one. And that is going to be 0, 1, 0, 0, 0, 0, 0, 0. Okay, so minus 75 or 0.75 is going to be 1, 0, 1, 0. Now we have to multiply these two. This is 0x5000. This is 0x(a)(0,0,0). Do you remember how we multiplied two binaries that were signed, and one of them was, well, the second was negative? We covered that yesterday. Please.
Basically, if you take one of the values and you add it to itself, shift it by one, depending on whether like the value of the other one is 1 or 0.
Mm-hmm. If the second number is negative, you had to do one last step. What was that?
You also do like the, I guess, two complements.
Of the last row.
Yeah.
Exactly. Okay. So then the 32-bit, if you do what he said, right? This is what you get. So if you do 500 multiplied by 0x(a)(0,0,0), then this is going to be 0x(e)(2) 0, 0, 0, 0. 1, 2, 3, 6 of them. Okay. And then you can, there is no way I write 32 0 ones here. Okay, so this is the hex. Now we need to find this, and this is in Q. So this is the important one. To understand that this is going to be the right result, it will give you the right result if you interpret it in the right Q format. The Q format you should be using when you're multiplying 115 by 115 is 230, right? Okay. So now when we interpret it in that, then, so in Q 2.30, this is going to be minus 5,316,480 over 2 to the power of 30, and that's going to be, got it here, minus 0.46875. So now let us do this multiplication in decimal. 625 minus 75. So always do that so you know what you should be expecting, and then, you know, then it gives you an idea if the interpretation or the binary calculation you did was right or not. 46,875. So we got the right answer. Please.
When multiplying, if one number is positive, one number is negative, into two's complement, instead of doing like separate cases, could we just keep track of the sign and turn the negative one to positive, and then do the normal multiplication, and then add all the sign later?
Like treat the two decimals as positives. Are you saying that? Like,
Yeah, like
start from the beginning?
If you have two binary numbers,
Yes.
one is positive, one is negative.
Yes.
When we're doing the multiplication, you know, probably like cases if first is negative or second is negative.
Yes.
Instead of doing that, can we just inspect and see is the final result going to be positive or negative, and just turn everything positive, do the multiplication, and then turn the result positive or negative depending on, you know, what we interpreted.
Do you remember the -3 and -5 we did together last session?
Would that not work? If you did
It didn't, right? Like we did -3 multiplied by -5 as if they were positive, and then the number we got was showing the sign bit to be 1, which is a negative number, but the result should be plus 15.
No, so like instead of
Oh.
directly doing the computation, could be done 2's complement both -3 and -5.
Uh-huh.
So interpreted as 3 times 5.
Yes.
And as we know, the final total is going to be positive.
Yes.
Just keep it up.
Oh, I have to do the calculation. I don't know if I can't. Yeah, I don't know right now if it's going to be correct. If you do like a regular 3 multiplied by 5, like as if they're two positive numbers, right? I don't know. We have to do it. How much time do we have? Okay, so let's solve the next one, because this is kind of like an engineering question rather than calculation. It says design a Q format for a system requiring a range of plus minus 50, so that's 100, and then a resolution of 0.01. That can be a voltage you're reading, right? So you want to know how you should be reading these voltages so that you have enough resolution and you can cover all of the range that you have. Okay, so what should I do next? Any ideas? Anyone else? Anyone? You? Do you want to give it a try?
Okay.
Yeah.
I think my idea is we can probably start from the resolution.
Uh-huh. Perfect. What is when you have, so we need to find Q m dot n, right?
Yeah.
So what was the resolution formula? She's on the right path.
X minus 2.
Exactly. So 2 to the power minus n. This resolution, we want it to be better than what? The question is telling us for it to be better than or 0, 1, right? Better means smaller. This has to be, gives us a smaller resolution, that's 0.01. And then I can say this has to be the other way, 100, and then say n must be log of 100 in 2, and that's, I think, 6 point something, if I know. Let me see. I don't know. This is I think 6 point something, 24, if I'm not mistaken. And this is. So that means, since it has to be an integer, so n equal to 7 would give us this resolution. Right? Now we want a range. The range that is asking us is between minus 50 to 50, right? I remember the range we were getting from m dot n was mostly dictated with m, right? Because we had the range to be minus 2 to the power of m minus 1 to m minus 1 minus 2m. That was the range we wanted. Assuming that this is going to be very small, let's forget about that. And then just find an m that would cover our 50 to minus 50 to 50, right? So 2 to the power of m minus m better be more than 50. So m minus n, m minus 1 is better than log of 50 into. And I think that's 5 something. Do I have the result here? Oh yeah. I found it. It's 664. And this is going to be 5.64. So m is more than 6.64 again, and then m is going to be better. We can say 7. If you had 7 bits, that would be enough. So the minimum we need for m is 7 bits, and then for n is 7 bits. So in total, since this is a sign, by the way, we need 1 bit for the sign as well, right? So in total, how much do we need? 1 bit for the sign. Do you see it? No. 1 bit for the sign. 7 bits for integer, or for resolution that we wanted. And then 7 bits for our range or our fraction. I said it reverse, but you got it. So that's 15 bits. If you want to stick with the, the standard versions, then it has to be Q dot what? Q what dot the what? Uh-huh.
Q
8.8. A standard one, right? We have total 16 bits. Go ahead.
Do you always treat kind of the range loss on the smaller side as like negligible in comparison to the
If the requirement gives you a symmetric one, then you kind of have to, right?
yeah.
Because this is not symmetric by calculation. So you can just, if the range it wants from you is a symmetrical one, then just go with whatever is larger. Because if you go with that side, then you end up with a smaller number,
Yeah.
and that misleads your M. Go ahead.
I don't think you have to add another 1 to your m. It's already taken into account when your range is 2 to the power of m minus 1. Like, because 2 to the power of 7 is way like
Where? This line?
yeah, I think doesn't that already include the sign? Like the plus 1 sign is included there, so there's a plus 1 afterwards.
Huh. I see.
Yeah, because with 7 bits, you can go from 0 to 127, right?
Yes.
So like that includes like minus 63 to minus 64 to 63.
So if we had here, you're saying if we had 7 here, or sorry, if I had 7 bits for the integer in the signed version, that would be minus 127 to 127.
With like, if the 7 includes the sign bit,
Uh-huh.
it should go from minus 64 to 63. something
Okay.
like that.
Oh, so you're saying that's enough?
Yeah.
Oh, okay. I see. So you're saying this, your comment is this M7 includes the sign.
Yeah.
Yeah, I see. You're right. So I don't need to add the sign bit. You're right. So I need 14 bits in reality. Right? Yes. So then, but still, the standard we should use is Q8.8. Do you see? Because those are the minimums. Yeah.
Why is n 8 not 7? N, not n.
So we said n that we need is 7, right? Minimum, right? So in the standard form, if you wanted to write this in the standard forms that we have, we use 8. Remember the standard ones we
I
had
thought
here?
that was only for the n. Like, why do we need to have an extra for the n as well?
This one? Again, just because the standards we have is like 8 bits fraction and then 8 bits for integer and
Oh, so we're adding that extra bit just
yes,
to
just so
save. Okay.
yeah. Minimum you need 14 bits.
Okay.
Yeah, that's okay.
Yeah.
But then the standard form is 16, and then the closest you have is 8.8. Yeah.